Hello all, this is Amrutha, 20MSP0019, presenting before you. Today, let's have a discussion on Fermi energy of electrons in a metal. So that's what my topic is about. So let's start with Fermi-Dirac statistics. Fermi-Dirac statistics was developed by Enrico Fermi and Pam Dirac. The statistics is applied to systems which are identical, indistinguishable, and those having half integral spin angular momentum in units of h cross. Most importantly, they obey Pauli's exclusion principle, which states that no two electrons can have all the same four quantum numbers. And also, the wave function of the system is anti-symmetric under the positional exchange of any two particles. So all these 4 points listed above forms the basic postulates of Fermi-Dirac statistics, and the particles obeying this particular statistics are called as fermions. Examples include electrons, protons, neutrons, positrons, etc. Then, the probability that a fermion can occupy a particular energy state E is given as f of E, which is defined as n of E by G of E, where n of E is the total number of electrons in the energy level E, and G of E is the density of states in that particular energy state. So f of E function is given as 1 over e to the power alpha into e to the power beta E plus 1. So in statistical equilibrium at absolute temperature, it is found that alpha and beta has the values alpha is equal to minus EF by KT and beta is equal to 1 over KT. So substituting the values of alpha and beta, we get the f of E function as 1 over e to the power E minus EF by KT plus 1, where EF will be the Fermi energy and K is the Boltzmann constant, which has the value 1.38 to 10 to the power minus 23 joule per Kelvin. Now, let's talk about the density of states. So, density of state means the number of energy states that is available per energy range. So, since here we are focusing on electrons, which will have two spin states plus half and minus half, so then the density of states would be twice the density of states of a single particle. That is what is given here. So, the density of state G of E will have the form 1 by h cube into 8 pi v root of 2m into m, where v, m and e will be respectively the volume, mass and energy of the particle under consideration. Okay, now we talked about Fermi energy. Like in the equation, we introduced a new quantity or new parameter which was called as Fermi energy. So now let's discuss what is Fermi energy. So now let us look at this diagram. At absolute zero temperature, that is at T equal to 0 Kelvin, all the lower energy states are filled completely, as you can see in this diagram. The delocalization of electrons strictly obey the Pauli's exclusion principle, because you know in the Fermi-Dirac statistics, the fermions obey the Pauli's exclusion principle. So all the capital N electrons, if there are capital N number of electrons, then all these N electrons, they get accommodated up to a certain level. And we can see that after this certain level, all the energy levels are empty. Okay, so the energy levels up to which the energy states are completely filled at 0 Kelvin and above which the energy states are completely empty. So that particular energy level is what we call as Fermi energy. So now let us discuss, or let us focus mostly on what happens when temperature becomes 0 Kelvin. So if suppose we are taking the condition when the temperature is 0 Kelvin and we assume that the energy of the particle is equal to EF, E is equal to EF, then at such a situation, when we are substituting the values in the probability distribution function, then what we'll be getting will be 1 over e to the power minus infinity plus 1, which will be nothing but the function will have the value of 1. That means when we are plotting this particular plot of f of e and energy, then the function will have a sort of step function. The plot will be in the form of a step function which has a value of 1. So also if f of e is equal to 1, then we can arrive at a condition that n of e is equal to g of e. That is, the total number of electrons is equal to the total number of single particle energy states. Now, our aim is to find what is the Fermi energy of these electrons in the metal. So to find that, first we have to find the total number of electrons in the metal, that is n of e. Suppose that the energy of the electrons are ranging from E to E plus dE, then the total number of electrons n will be, because in this case where we are varying the temperature, like temperature is 0 Kelvin, so at that case we have seen that the energy levels are from the lowest energy level to the maximum energy level is Fermi level, that is a Fermi energy level. So we have to integrate from 0 to the Fermi level n of e dE. But we also know that n of e is equal to g of e. So instead of n of e, we can write it as g of e. So from the earlier equation, we have already got the density of states of the electron. So that we have substituted here. So from this expression, we can see that all the constants, v, m, and everything, h are all constants. So the integration is a function of root e alone. So after integration, we'll be getting something like when we solving, we'll be getting something like EF raised to 3 by 2 divided by 3 by 2. So further, when we are rearranging it, we can get an expression where EF is given by h square by 8 term into 3n by pi v the whole to the power 2 by 3. Now, if suppose we are denoting capital N by V as small letter n, which is the concentration of electrons in the metal, then the expression for Fermi energy EF can be written as h square by 8m into 3n by pi whole to the power 2 by 3. So this particular expression can give you the Fermi energy of electrons in a metal. Okay, now that we have found the Fermi energy, we can find the total energy of electrons at this particular temperature, that is equal to 0 Kelvin. So that what we have to do is that we have to multiply the obtained n of e with the energy E. So again, as similar as before, the n of e is replaced by g of e. We substitute the value of g of e. And here again, we see that the integration becomes a function of e to the power 3 by 2. So again, when we are doing the integration and when we are simplifying, we see that the total energy of the electrons at t equal to 0 Kelvin reduces to the form 3 by 5 times NEF. If this is the total energy, then the average energy per electron at t equal to 0 Kelvin will be E total divided by N, which will be 3 by 5 times EF. Now, what are the interpretations that we can derive it after doing this derivation will be? The Fermi energy of electrons solely depends on concentration. That is what we can see in the previous slide, where here you can see in the equation number 4, all the other values, h, 8, m, 3, pi, everything are constants. So we can see that EF only depends on n. It is directly proportional to n to the power 2 by 3. So we can say that the Fermi energy solely depends on the concentration of the electrons in the matter. And it is seen that here we have calculated the total energy at t equal to 0 Kelvin. So classically, we assume that the total energy of any system at absolute zero temperature will be 0. That is what classically we expect. But Fermi-Dirac statistics gives us an idea, or it showers the idea of quantum nature. That is, there exists some energy EF even at t equal to 0 Kelvin. That is what we can see here as the total energy as t equals 0 Kelvin is given as 3 by 5 times NEF. Now, the average energy per electron again is 3 by 5 times the Fermi energy at absolute zero temperature. Now, this Fermi energy concept is very crucial. So, Once you know the Fermi energy, it is very easier to find any other parameters also, like the Fermi temperature, which is defined as the temperature that is equivalent of Fermi energy. It can be found by the expression Tf is equal to Ef by K. Or also the ground state pressure of the electron gas P, which is given by the expression 2 by 5 times NEF. So what I'm coming to say is that once you know the EF, the Fermi energy of the system, then a lot of parameters could be made up from this simple Fermi energy. So I hope this session was informative, and I hope it was more interesting and you could get some more information about Fermi energy and the Fermi derived statistics. So thank you, and sincere thanks to Bhaskar Sen Gupta sir for giving me this opportunity. Thank you once again.